In the darkest hours of the night, when the world seems to quiet down, there's an unseen hunter gliding through the air with remarkable precision. Nocturnal and elusive, these creatures have unlocked one of nature's most sophisticated secrets, the ability to see with sound. Today, we explore how bats use echolocation to navigate and hunt in complete darkness, an ability that has inspired modern technology and continues to amaze scientists. Over 50 million years ago, bats developed a game-changing adaptation, echolocation. This remarkable ability allows them to create a mental map of their surroundings using nothing but sound. Echolocation is present in over 1,000 bat species across multiple families, allowing them to thrive in environments where other predators would struggle. It's an ability that has also evolved in other animals, such as toothed whales and some birds. For bats, this adaptation opened up an entirely new ecological niche, enabling them to hunt at night when other predators relying on vision couldn't compete. This evolutionary trait allowed them to diversify and spread across the globe. Bats produce ultrasonic calls, frequencies far beyond human hearing, ranging from 20 to 200 kilohertz. These sound waves travel through the air, reaching speeds of about 343 meters per second. As these waves spread outward, they interact with objects in the environment, bouncing off surfaces and returning to the bat. The returned echoes carry vital information: the size, shape, texture, and movement of everything they encounter. Bats' ability to process these echoes is nothing short of extraordinary. Their brains are finely tuned to analyze these returning sound waves with precision. When a bat sends out a call, it measures the time it takes for the echo to return, calculating the distance of objects with millimeter-level accuracy. In addition to time, bats analyze changes in the frequency of the sound waves. These shifts, known as Doppler shifts, help bats determine not just where an object is, but also how fast it is moving and in which direction. The strength of the echo gives the bat clues about the object's size, texture, and composition. For example, a bat can distinguish between an insect flying through the air and a tree branch using the amplitude of the returning sound wave. The brain's ability to process this information is remarkable, as it devotes significant neural resources to acoustic processing. Specialized regions of the bat's brain are dedicated to analyzing these echoes, allowing the bat to build an incredibly detailed and accurate mental map of its surroundings. When a bat begins a hunt, it follows a clear set of phases: the search, approach, and terminal phase. During the search phase, the bat emits slower, longer calls at a low rate, about 10 to 20 calls per second. This helps it gather a broad acoustic view of the environment, scanning for potential prey. Once the bat detects an insect, it moves into the approach phase, where the call rate increases to up to 50 calls per second. The calls also become shorter, focusing on gathering more detailed information about the target. Finally, in the terminal phase, just before the bat captures its prey, the call rate accelerates dramatically to as much as 200 calls per second in what is known as a feeding buzz. This rapid-fire sound emission allows the bat to hone in on its prey with pinpoint accuracy. Bats use different echolocation strategies depending on their species and environment. Some species, like the forest-dwelling brown long-eared bat, use frequency-modulated FM calls that sweep from high to low frequencies, providing excellent spatial resolution. Others, like the horseshoe bats and mustached bats, rely on constant frequency CF calls, which maintain a steady frequency with short FM components. These calls are superior for detecting moving prey through Doppler shifts. Some bats, like the barbastel, employ stealth echolocation, emitting extremely quiet calls that prevent moths from hearing their approach, allowing them to hunt undetected. While echolocation is an incredibly effective tool, it does have its challenges. One of the most significant issues occurs when multiple bats hunt together in the same area. Their calls can interfere with each other, causing a phenomenon known as jamming. To combat this, bats adjust their call frequencies to create unique acoustic fingerprints, allowing them to distinguish their own echoes from those of other bats. Similarly, bats face challenges from prey that have evolved to evade them. Some moths, for example, have developed the ability to hear bat calls and perform evasive maneuvers, or even produce confusing clicks to throw the bats off track. To overcome this, bats have adapted by hunting in stealth mode, emitting quieter calls, or using frequencies that are outside the range of moths' hearing. Environmental factors like rain, dense vegetation, and background noise can also complicate echolocation. When echoes are obscured by such factors, bats rely on a combination of other senses to compensate. They integrate visual, olfactory, and even magnetic cues to maintain their navigation abilities when echolocation becomes less reliable. Echolocation has had a profound influence on human technology. The principles of bat echolocation inspired the development of sonar sound navigation and ranging during World War II, specifically for submarine detection. Since then, echolocation has influenced various technologies used today, including radar, medical imaging, and even assistive devices for the visually impaired. In the realm of modern technology, sonar systems are used to detect objects in underwater navigation, while radar systems help vehicles detect obstacles. Self-driving cars, for instance, rely on lidar light detection and ranging and radar, both of which are based on echolocation principles to navigate in low visibility conditions. Medical imaging, such as ultrasound, also uses the same basic principles to create images of the internal structures of the human body, providing non-invasive diagnostics. Additionally, assistive technologies like the ultracan have been developed to help visually impaired people navigate their environment using ultrasonic pulses and tactile feedback. Looking forward, the future of echolocation-inspired technology is incredibly promising. There are efforts to create miniaturized drones that navigate without GPS, relying on echolocation-like systems to maneuver. Advances in underwater exploration equipment are also being driven by these principles, and the potential for more precise medical imaging continues to grow. The idea of smart buildings, where movement is detected through echolocation, is another exciting possibility. The sophistication of bat echolocation still far exceeds our technological capabilities in many ways. We have so much more to learn from these remarkable creatures. In conclusion, bats' ability to navigate and hunt using echolocation is not only a testament to their evolutionary brilliance, but also a source of inspiration for innovations in human technology. As we continue to explore the depths of this ability, we must also recognize the importance of conserving bat populations, as they are not just crucial to the health of ecosystems, but also to the continued development of technologies inspired by their extraordinary senses. By protecting bats, we are safeguarding a biological blueprint that could lead to future breakthroughs across a wide array of fields. Bats are nature's sonic navigators, masters of the dark, and as we look to the future, it's clear the question is not just how we can learn from them, but how much more there is to discover. Thank you for watching. If you enjoyed this deep dive into the world of bats and echolocation, make sure to like, subscribe, and hit the bell icon for more insights into the wonders of nature and technology.